Well, today we will discuss the eigenvalues of the path Pn. We will first recall the eigenvalues of the cycle Cn. So this is recall. This we had done in the previous lecture. For n greater or equal to, the eigenvalues of cycle Cn are this was given by twice cos pi k by n, where k is equal to 1, 2, up to n. Now, in this lecture, we will discuss the eigenvalues of the path Pn, but before that, we will take up a proposition. So, proposition. Let lambda be an eigenvalue of path Pn and with x equal to x1, x2, xn as the corresponding eigenvector, as the corresponding eigenvector of Pn. As the corresponding eigenvector of Pn, then for n belonging to n, the vectors say the vectors x1, xn, then 0, minus xn, so on, minus x1, 0, and 0, x1 to xn, then 0, minus xn to x1. x1, which is minus x1. Then for n belonging to n, the vectors this and this are the linearly independent eigenvectors of the cycle graph C 2n plus 2 corresponding to the eigenvalue lambda. Corresponding to the eigenvalue lambda. So what is this proposing? It says that if we have a path Pn and lambda is the eigenvalue of Pn with x equal to this as the corresponding eigenvector, then the same lambda is the eigenvalue of the cycle graph C 2n plus 2, and the corresponding eigenvectors are these two, and these are the two linearly independent eigenvectors corresponding to the eigenvalue lambda of Cn plus 2. Now let us do the proof of this result. So in the proof, let lambda be an eigenvalue of adjacency matrix of Pn, that is APn, and let x is equal to x1 through xn be the corresponding eigenvector. Be the corresponding eigenvector. Then what we have, then this A adjacency matrix of Pn into x, this will be equal to lambda times x, and this is by definition of the eigenvector. Now we will see how the adjacency matrix of the path Pn looks like. The adjacency matrix of path Pn is adjacency matrix of Pn is APn, which is equal to suppose Aij n cross n matrix, where this Aij, this is equal to 1 if I is equal to j plus 1 or j is equal to I plus 1, and this is equal to 0 elsewhere. That is, the super diagonal entries of APn are all equal to 1, and all the remaining entries of APn, super diagonal and the sub-diagonal entries are actually equal to 1, and all the remaining entries are equal to 0. So that is the entries on super diagonal and sub-diagonal of APn are equal to 1, and all other entries are 0 in adjacency matrix of APn. So this is how we define the adjacency matrix of the path graph Pn. Now we have this equation APn x is equal to lambda times x. So now APn into x1 through xn. It's 1 o'clock. Now this is defined to be equal to lambda times x1 to xn. Now this gives, now let's multiply this. Then the first equation that we obtain here is x2, this gives us x2 is equal to lambda x1. So let's write this some adjacency matrix here of the path matrix APn. So here the first row will be equal to 0, 1, 0, and all the remaining entries will be 0. And the second row will be 1, 0, 1, 0, and so on, that is 0. Then the third entry will be 0, 1, 0, 1, then 0, and so on, 0. And this is how the adjacency matrix of path matrix Pn looks like. Then here we are multiplying it with x1, x2, so on up to xn. So therefore, when we multiply the first row, only this A12 entry in the first row is non-zero, and all the remaining entries are equal to 0. So if you multiply the first row with this column vector, then we get x2. But now this is equal to lambda times x. So therefore, this is equal to lambda times x1. So therefore, x2 is equal to lambda times x1. Now, similarly, when we multiply the second row has this entry as non-zero and this entry as non-zero, and this will get multiplied to x1, and this entry will get multiplied to x3. So therefore, we have x1 plus x3, but now this equal to lambda times x2. And similarly, the third entry will be x2 plus x4. Now this will be equal to lambda times x3, and so on. Now similarly, we will obtain the n minus 1th equation here. That's x n minus 2 plus xn. This will be equal to lambda times x minus 1. And the last equation is x n minus 1 is equal to lambda times xn. Let's call the system as equation system number 1. So this is what we obtain by saying that x1, x2, xn is the eigenvector corresponding to the eigenvalue lambda. Now let y be equal to minus xn minus xn minus 1, so on, minus x2 minus x1. Then we will evaluate what is apn into y. Then A adjacency matrix or the path matrix Pn into y. Now this is equal to, let's write the adjacency matrix here. So it is 0, 1, 0, 0, 0, and so on. Then 1, 0, 1, 0, 0. Then all the remaining entries are 0. And similarly, the third row will be equal to 0, 1, 0, 1, 0, like this. And let's write the n minus 1th row. The n minus 1th row will have the structure like this. It is 0, 0, 0, 0, so on. If we write, suppose, 3 zeros here, then the last 3 entries in the n minus 1th row will be 1, 0, 1. And the last row in this matrix will be equal to so this will be 0. This is actually the entry n1 because and n1 and 1 n are not adjacent. This is the entry n2, n3, and the last entry will also be equal to 0. But the entry before that will be equal to 1 because that will be the entry n minus 1 is adjacent with n. And now this entry will again be equal to 0. And all the remaining entries will be equal to 0. So this actually the vertex corresponding row corresponding to vertex v1, this row corresponding to vertex v2 corresponding to vertex v3, this is the row corresponding to vertex vn minus 1, and this is the row corresponding to vertex vn. So this is apn, and now we have to multiply it with the row vector column vector y. Then y is defined in this way. So we have minus xn minus x n minus 1, so on, minus x2 and minus x1. So let's see what the system of equations that give us, that this thing gives us. Then when we multiply this first row here, we get minus x n minus 1. Now multiplying this row, we get minus xn minus x n minus 1. And similarly, multiplying this row, we get minus x n minus 1 minus x n minus 3. Now multiplying this row, we get minus so on, and this is minus, this will be minus x1 and minus x3. So this will be minus x3 minus x1, and the last will be equal to minus x2. So this is what we obtain. Now looking at what are the values that we can obtain from the system of equations given by 1. Now here this xn minus 1, this is lambda times xn. So here we have minus xn minus 1, so we can write this minus lambda times xn. Now the second equation is xn minus 2xn, this lambda times xn minus 1, so this is equal to minus lambda times xn minus 1. And similarly, this is minus lambda times xn minus 2 from the system of equations given by first. Now this minus x3 minus x1, this can be written as minus times lambda x2. So this is minus times lambda x2, and similarly this minus xn minus 1, this minus times lambda x1. So therefore what we obtain a pn into y. Now here we can take this lambda common. So this is lambda times, the first is minus xn, then minus xn minus 1, and so on, minus x2 minus x1. So therefore we can write this equal to lambda times y. And this equation implies us, so this implies y, which is defined as minus xn to minus x1, is also the eigenvector of APN corresponding to lambda. Now actually what we have to show that this vector is an eigenvector of C2n plus 2, and this vector is also an eigenvector of C2n plus 2, and these are the two linearly independent eigenvectors of C2n plus 2 corresponding to the eigenvalue lambda. So now define, suppose Z is equal to x1, x2 to xn, then 0, minus xn to minus x1. Then we have to show that this is an eigenvector of C2n plus 2 corresponding to the eigenvalue lambda. For this thing we will compute then this thing. Then adjacency matrix of C2n plus 2 into Z. We will see what is this equal to. So this is equal to adjacency matrix of C2n plus 2. Now this has to be multiplied with this column vector Z. So actually this is the column vector. In fact, we should also write the same in the statement. So this is the column vector. Now this is like this. So this is x1, x2, so on, xn, then 0, minus xn to minus x1. Now this equal. Now we know what is the structure of the adjacency matrix of a cycle graph on 2n plus 2 vertices. Now if we look at the first row of the cycle matrix, that is the row corresponding to the vertex v1. The first row of the adjacency matrix of C2n plus 2 is the row corresponding to the vertex v1. So let's first construct this C2n plus 2 here. So let this be vertex v1, this is v2, v3, v4, this is v2n plus 2, and this is v2n plus 1, and so on. Now the first row of adjacency matrix of C2n plus 2 is a row corresponding to the vertex V1. Now this vertex V1 is adjacent with V2. That means A12 entry is non-zero in this adjacency matrix, and also the last entry in the first row is non-zero. So therefore the second entry in the first row is non-zero, and also the last entry in the first row is non-zero. And in fact we had this last entry as 0 here. So we have the last entry as 0 here. We forgot to write it here. So this is 0 here. This is 0. So when we multiply the first row with this column vector, then the second non-zero entry in the first row is non-zero, so it will be multiplied with this x2, and then the last entry is non-zero, but that will be multiplied with a 0. So therefore the first entry in the column vector obtained by this multiplication is just x2. Now we will multiply the second row of the adjacency matrix here with this column vector. Now the second row is corresponding to the vertex V2, and V2 is adjacent with V1 and also adjacent with V3. So therefore the second row of this adjacency matrix contains two non-zero entries. One is at the position 1, 2, and second is at the position 2, 3. So when we multiply the 1, 2 position, it will be multiplied with this x1, 2 position. It will be the 2, 1 position. It will be multiplied with x1, and the 2, 3 position. It will be multiplied with x3. So here the second term we will obtain is x1 plus x3. Now the third row has two non-zero entries in this adjacency matrix, and those two non-zero entries are 3, 2 and 3, 4. So 3, 2 will be multiplied with x2, and the entry 3, 4 will be multiplied with x4. So it is x2 plus x4 here, and similarly so on. And when we reach the nth stage, similarly when we multiply the nth row, at the nth stage we will, the nth row of this adjacency matrix will be multiplied with 0 and minus xn minus 1. So it will be xn minus 1 plus 0. Sorry, this xn minus 1 plus 0. So this is the multiplication of nth row of the adjacency matrix with this column vector. And then when we multiply the n plus 1th row, it will give us the non-zero entry in this. The entry in this column vector will be xn plus minus times my xn. And similarly, the next term will be 0 plus minus times xn minus 1, and so on. And the last entry will be like minus x1 minus x3, and similarly then the last entry will be x2. So this is the column vector that we obtain when we multiply the adjacency matrix of adjacency matrix of C2n plus 2 with this column vector. But now looking at the system of equations which was given by the path matrix. So looking at this system again, this x2 is equal to lambda x1. So therefore this first x2 we can write this as, this is lambda times x1, and similarly here minus x2, this we can write as minus lambda times x1. And similarly here this will be lambda times x2, and the last one will be equal to minus lambda times x2, and so on. Then we will get to lambda xn. Then the next will be lambda times 0, because this xn plus minus xn is equal to 0. And then the next term will again be minus xn minus 1. This will again be equal to minus times lambda xn, and so on. But we can see, we can take the lambda common, so it is lambda times z. Now when we take lambda common, we will get x1, x2, xn, then 0. then minus x, and so on up to minus x1, and the last entry in fact will be equal to 0 here. So this will be 0. So therefore, we have seen that this z is an eigenvector of C2n plus 2, and the corresponding eigenvalue is lambda. Similarly, in the similar lines, we can show that similarly the z dash, which we shall define by 0, then x1 through xn, then 0, minus xn through minus x1, and this transpose is also an eigenvector of C2n plus 2 corresponding to lambda. So thus we have shown that this z and z dash were the two eigenvectors of C2n plus 2 corresponding to lambda, where this x1, x2, xn was the eigenvector of the path Pn corresponding to lambda. Now using this proposition, we can find out the eigenvalues of the path matrix, adjacency matrix of the path graph. So now the theorem for n greater or equal to 1, the eigenvalues of adjacency matrix of path Pn are given by twice cos pi k by n plus 1, where k runs from 1 to n. Okay, now let us do the proof. Let lambda x be the eigenpair. Let lambda x be the eigenpair of adjacency matrix of path Pn, where x is equal to x1 through xn. Then from the previous proposition, then this y is equal to, or we just don't need the y now, we just need then z, which was defined to be equal to x1, xn, then 0, then minus xn through xn 0, and z dash, which is equal to 0, x1 through xn, then 0, minus xn through x1 are the eigenvectors then these are the eigenvectors of C2n plus 2 corresponding to lambda. Corresponding to lambda, where this lambda is actually an eigenvalue of the path matrix P, and in fact we can clearly see that these are the two linearly independent eigenvectors of C2n plus 2 corresponding to lambda. So actually by proving this thing, what we have established is that we have established that this lambda is an eigenvalue of C2n plus 2, and it has two linearly independent eigenvectors corresponding to it. So we have thus established that we have established that for each eigenvalue lambda of Pn that each eigenvalue lambda of Pn must be an eigenvalue of C2n plus 2, must be an eigenvalue of C2n plus 2 with geometric multiplicity equal to 2. So since we have seen that lambda was an eigenvalue of the path matrix, and now it is an eigenvalue of the C2n plus 2, and these are the two linearly independent eigenvectors corresponding to it in the adjacency matrix of C2n plus 2. So this means that lambda is an eigenvalue of C2n plus 2, and its geometric multiplicity is equal to 2. But since this adjacency matrix of C2n plus 2 is symmetric, and since every symmetric matrix is diagonalizable, and for a symmetric matrix, AM, that is the arithmetic multiplicity for any eigenvalue lambda, is always equal to GM of the eigenvalue lambda. Since we have shown that geometric multiplicity of lambda is equal to 2, so thus arithmetic multiplicity of lambda is equal to 2. So therefore, every eigenvalue of the path matrix Pn is actually the eigenvalue of C2n plus 2 of multiplicity 2. So therefore, we can find out the eigenvalues of the path Pn from the eigenvalues of C2n plus 2. And they are those eigenvalues from C2n plus 2 whose arithmetic multiplicity is equal to 2. So that's we have shown that, we have shown the eigenvalues of C2n plus 2 with AM equal to 2 are the eigenvalues of adjacency matrix of the path Pn. So we will now just look for the eigenvalues of C2n plus 2, and that will give us the eigenvalues of path Pn. Now, eigenvalues of adjacency matrix of C2n plus 2 are, and these we have obtained in the previous theorem. Now they are given by twice cos 2 pi k by 2n plus 2. And this can be written as this actually equal to twice cos pi k by n plus 1, where k runs from 1 to up to 2n plus 2. So we see the eigenvalues, thus the eigenvalues of C2n plus 2 are thus the eigenvalues of C2n plus 2 are, it is twice cos pi k by n plus 1, where k runs from 1 to up to 2n plus 2. Now let's list these 2n plus 2 eigenvalues first, and then we will see what are the eigenvalues that have arithmetic multiplicity 2 in this list. When we put k equal to 1, so we get the eigenvalue is twice cos pi by n plus 1. Then for k equal to 2, it is twice cos 2 pi by n plus 1, and so on. When we put k equal to n, we get twice cos n pi by n plus 1, and then put k equal to n plus 1, we get twice cos n plus 1 pi by n plus 1. Now next we will put the remaining values of k. So next we have to put k equal to n plus 2 and then n plus 3 and so on. But so therefore up to this stage what we have used the values of k like this. So we have used k is equal to 1, 2 up to n plus 1. Now the remaining values of k are k is equal to n plus 2, then so on up to 2n plus 2. But now for the remaining values of k, we will make the list in the reverse order. So first we will substitute the value of 2n plus 2 and write it here. So then for k equal to 2n plus 2, we will get, suppose, something like twice cos 2n plus 2 pi by n plus 1. So this is the eigenvalue obtained for the value of k equal to 2n plus 2. Now the value of k equal to n plus 2. So therefore here we will write the eigenvalue corresponding to n plus 2. Then this will be twice cos n plus 2. Okay, so let's make the list in this way. Let's write this twice cos here. This is twice cos n plus 2, then pi by n plus 1. Then similarly, the next one will be twice cos n plus 3, then pi by n plus 1, and so on. Now when we look at this eigenvalue, now this eigenvalue, this one, this is actually equal to twice cos just pi, because n plus 1 and n plus 1 cancel, so this is equal to minus 2. Now this last eigenvalue here, now this eigenvalue, this is actually equal to twice cos 2 pi, because we can take the 2 common and then n plus 1 and n plus 1 cancels here, so we get twice cos 2 pi, and this is equal to 2. So therefore these two eigenvalues are two distinct eigenvalues and they are not repeating. But now we can see that, let's write one more eigenvalue here, which is before this last term here. So that will be twice cos 2n plus 1 into pi by n plus 1. Now we will see that how this list of 2n eigenvalues are not actually the only number of distinct eigenvalues. Among this list of 2n eigenvalues is n plus 1. So there are, this list of 2n eigenvalues is actually the set of only n eigenvalues. Now we have to look for what are the eigenvalues which are repeating, and how these two lists is actually the same list of eigenvalues. Now let's look for this situation. So now we will see that we will compute what is cos 2n plus 1, 2n plus 2 minus k upon n plus 1. Let's see what is this equal to into pi. Now this is equal to, and this is actually the last eigenvalue. This is the eigenvalue in this list when it is calculated, when it's counted from the reverse order. So this is 2n plus 2 minus k. This one is 2n plus 2 pi minus 0. Then this is 2n plus 2 pi minus 1 times pi. And similarly, this is actually here, this 2n plus 2 minus k by n plus 1. This represents an eigenvalue in this list of eigenvalues in the reverse order. But when k is equal to 1, this gives us this eigenvalue. K is equal to, this gives us the second eigenvalue in this list of eigenvalues, except actually excluding these two. So we will just look for this eigenvalue. So this is the first eigenvalue in the reverse order, and then we have the second eigenvalue. This will be the k minus 1 eigenvalue, and this will be the eigenvalue number k in the reverse order. So this is what we obtained for k equal to 1, and the eigenvalue which is before this one will be obtained for the value k equal to 2, and this will be obtained for k equal to k minus 1, and this will be actually the kth eigenvalue from the reverse, which is obtained, which is actually this number. So now let's see what is this equal to. The kth eigenvalue in the reverse order. Now, and this is equal to cos. We can split it. This is 2n plus 2 upon n plus 1 into pi, then minus k times pi upon n plus 1. But now this is equal to cos. This is n plus 1 cancels here, so it is just 2 pi minus k pi upon n plus 1. But now cos 2 pi minus this thing, by periodicity of cos, since 2 pi is the period, this is actually equal to cos pi k upon n plus 1. So actually what this equation tells us, that now see, if we put k equal to 1 here, we will get this first eigenvalue. When we put k equal to 2 here, we will get the second eigenvalue. And similarly, when we put k equal to n here, we will get this nth eigenvalue. But at the same time, when we put k equal to 1 here, we will get this eigenvalue, but in the reverse order. K equal to 2 here, we will get this eigenvalue, and so on. So therefore, this list of eigenvalues and this list of eigenvalues is actually the identical list, but in the reverse order. So therefore, this first eigenvalue is actually equal to this last eigenvalue here. This one is equal to the second eigenvalue from the last, and this last eigenvalue n pi, this is actually equal to this eigenvalue. So therefore, this is how these two lists of eigenvalues are identical. So thus for k equal to 1 to up to n, the eigenvalues cos pi k by n plus 1 have arithmetic multiplicity 2. Arithmetic multiplicity 2 in the list of eigenvalues of eigenvalues of adjacency matrix of C 2n plus 2. So thus the eigenvalues of path P and R, thus the eigenvalues of adjacency matrix Pn are actually this twice here. It is twice cos pi k by n plus 1, where k is equal to 1 to up to n. So therefore, we have completed the proof of evaluating the eigenvalues of the path Pn. With this, we conclude today's lecture. Thank you so much.